All right, part 2 of the first section still. We're still focusing on sequence. I have our first theorem here, and there's going to be a lot of theorems in chapter 10. So let there be two different sequences, A sub n and B sub n. Be sequences, and let A and B be real numbers such that, so we're just kind of setting up the theorem here. We're setting it up so that A sub n converges to A and B sub n converges to B. So we have two sequences that we know converge. There's a bunch of different properties that we can then say about this. The first one's called the sum rule. What the sum rule says is that if you take the limit as n goes to infinity, of the two sequences added together, A sub n plus B sub n, this is going to converge to the two limits added together. So if you add the sequence values together independently for each index, then whatever the sequence does, it still converges to the sum of the two limits. All right, and the rest of these are similar. So we have the difference rule. I'm going to shorthand it a little bit and just rewrite this as A sub n minus B sub n. This in total, if you do this again index by index, is going to converge to the two limits subtracted from each other. The constant multiple rule. The constant multiple rule says that if you multiply a constant onto either of the sequence values, it converges to just that constant times the limit. So you can take constants in and out of your sequences. We do have a product rule. So here's where we really need to start being careful because we are going to eventually get into series, and the product rule is not true for series, but for sequences it is. So if I multiply the sequence values together index by index, it still converges to the product of the limits multiplied together. And if we have a product rule, then usually we also have the quotient rule. So this just says the same thing. But if you have A sub n divided by B sub n, it converges to A divided by B, as long as that B is not 0. All right, now that we have these properties, we can answer a few more questions and look at some more homework examples. So the first one we'll look at is let's try to find the limit as n goes to infinity of the value n minus 1 over n. Okay. Cool. At the end of this section, we're going to get to a very easy way to do these, but for now we're using these rules. What we would do here is that we would break this up, still doing the limit as n goes to infinity. I have two terms up top and then just a single term in the bottom, so I'm going to divide each of these by n. N divided by n is 1. That's going to be minus 1 divided by n. So I'm just rewriting my quotient like this. Now I have two sequence values that are subtracted from each other, so now we have the difference rule. Here I could write this as the two different limits. So the limit as n goes to infinity of the first sequence 1, that's all going to be minus the limit as n goes to infinity of the other sequence 1 over n. Each of these is something that we've already proved. We've looked at the limit of a constant. The limit of a constant just goes to that constant. Minus the limit of 1 over n is also something that we've seen. That goes to 0, which means that the limit of n minus 1 over n goes to 1. And I hope you can kind of see that. Just plug bigger and bigger numbers into this n and you'll see that it approaches that. I do have one more example here, a little bit more complicated. So let's look at, I'm going to ignore the limit stuff. Just know that it's the limit as n goes to infinity. So the limit of 4 minus 7n, 4 minus 7n to the 6th divided by n, I hope that's to the 6th. I can't read my own handwriting, plus 3. Great. Okay, so I know that looks really bad, but believe it or not, we can use all of the rules up top there to break this thing down. And I'm just going to do this all in one go instead of doing it bit by bit. We're taking the limit as n goes to infinity of all of this. Those n to the sixes are troublesome and kind of in the way. So a trick for doing these is whatever the biggest exponent is on your variable n is to divide by that. So we're going to divide the numerator and the denominator by n to the sixth. When you divide the top by n to the sixth, we are going to have 4 divided by n to the sixth, but that's just going to be minus 7 because the n to the sixths cancel out. When I divide the denominator by n to the sixth, I'm going to get 1 plus 3 over n to the sixth. Now maybe you can see what this limit is going to go to. At this point, I can evaluate the limit. If n is going to infinity, then on this first fraction, 4 over n to the sixth, that's going to go to 0. This is just a constant, so as n goes to infinity, it stays at that constant, negative 7. The 1 is a constant, so that stays at 1, plus 3 over n to the sixth as n goes to infinity goes to 0. So I get negative 7 over 1, or just negative 7. Okay, so just using these properties. All right, moving on from there, let's look at a few more theorems here. Like I said, Chapter 10 is just packed with them. This one's called the sandwich theorem. I'm sure that you've heard of this one before from Calc 1. This is the sandwich theorem of sequences. You probably saw the sandwich theorem of limits in Calc 1. So let there be 3 different sequences, a sub n, b sub n, c sub n. Of real numbers if we have that every single value of a sub n is less than every single value of b sub n is less than or equal to every single value of c sub n is true or holds for all n beyond some index capital N, and if we have that a sub n converges to some value L, and c sub n converges to some value L, then we automatically get that b sub n converges to that same value L. Okay, so again, the sandwich theorem, or sometimes it's called the squeeze theorem, if there are 3 sequences, and you always have it that A is less than or equal to B is less than or equal to C, and, beyond some index, that doesn't always have to be true, but as long as it's true eventually, if A and C, the outside sequences, converge to a certain number, B converges to that same number. Okay, I have a couple more theorems here, and these are the big ones, the important ones. Not to say the sandwich theorem isn't important, but it's not as important. So this one is called the continuous function theorem for sequences. And it says this, so again, same setup as always. Let a sub n be a sequence of real numbers if we have that a sub n converges to L, and if f is a function continuous at L and defined at all a sub n, then we also get that f of a sub n converges to f of L. Okay, so just looking at this, it might not seem very important, but it is, and I'll show you why here in a second. Let a sub n be a sequence of real numbers if a sub n converges to L, and if f is a function continuous at L and defined at all a sub n, then the sequence f of a sub n converges to f of L. And it's best to show how this works with an example. Let's say we have the limit as n goes to infinity of the square root of n plus 1 over n. Okay. We don't have anything that tells us what to do with square roots or anything crazy like that. However, if we think about this square root as the function f, we already know what the inside of that converges to. We did this one earlier. N plus 1 over n converges to 1. What that means is that the inside of a function converges to something, then the entire thing converges to the function evaluated at that limit. So this is just going to converge to the square root of that limit 1 or just 1. All right, so again, just to kind of reiterate that, if you have a sequence of something that you know converges and it's applied by a function on the outside, then just figure out what the limit of the inside is and then evaluate the outside function on that limit. All right, I have one more really important theorem, and then we'll be done. Oh no, so there's a little bit more. I'll make another video. So one more theorem I want to do in this video. Suppose that f of x is a function defined for all x greater than or equal to some starting index value, whatever that happens to be, n sub naught. And let's say that again a sub n is a sequence of real numbers, such that a sub n is equal to f of n for n greater than or equal to that starting location. Then we get the following. If the limit, I have to be a little bit more careful here, so let's write this one out. This is the limit as x goes to infinity of f of x equals L. This gives that the limit as n goes to infinity of a sub n also approaches L. All right, just to read through it and then we'll talk about it. Suppose that f of x is a function defined for all x greater than or equal to n sub naught, and a sub n is a sequence of real numbers such that a sub n equals to f of n for n greater than or equal to n naught. Then, if the function, the limit of the function f of x equals L, this gives that the limit as n goes to infinity of a sub n equals L. All right, what this is saying is that if you have a sequence and if you replace the index of that sequence with the variable x and it becomes a continuous function, then we can just treat our sequences as continuous functions. All right, this will be better explained when we get into some examples. These examples can be a little bit long, so I'm going to make them in the next video.